First of all, thank you to the organizers. It's a really nice conference. I've enjoyed all the papers. A couple of warnings. I'm at home in Delhi, so, you might hear street noise and dogs barking and stuff like that. Also, a small chance that, that the internet or the electricity will fail. This is the monsoon. If it does, I hope it doesn't, I don't know, I'll try and use my hotspot or something. But anyway, so this is a paper with several co-authors, Ujjwal, Sauvik, Sonal, and Bhasha. They're all students of mine, except Ujjwal, who is a grad student, a student of a student. This is a paper about strategy-proofness. It's kind of a follow-up paper to a paper that all of us wrote, on what it's based. It's a relatively short paper, so I'm not sure I can exhaust all the 40 minutes. So I begin with the obligatory slide about strategy-proofness, which is kind of redundant for this audience, but let me just say it. So we look at a model where agents have private information, which are their types, and they have a collective goal specified by a social choice function that depends on private information. And the basic question is, what are the social choice functions that are achievable, that is, provide agents the incentive to reveal their private information truthfully. And so incentive compatibility guarantees that every agent reveals her private information truthfully, irrespective of the announcement made by the other agents. So, speaking more formally, if the set of agent types is T, strategy-proofness means that no agent of type small t in capital T can be better off by reporting any other type T prime. So, so this paper and the paper before it is motivated by the observation that agents of a type will only check whether or not she can be better off by reporting to a type T prime, which is in some set E of T. And we think of E of T as the set of types that are local for T. And the fundamental question is, under what conditions is requiring incentive compatibility, or local incentive compatibility, that is failure to gain by a deviation to a local type, when is this equivalent to strategy-proofness? So just jumping ahead a little bit, in our earlier paper, we provided a sort of a complete characterization of this equivalence for sort of arbitrary sets ET, for an arbitrary notions of localness. And what we are showing in this paper is that if you impose a slight or mild unanimity condition on the social choice functions under consideration, then in fact the condition weakens considerably. So a much weaker condition is is sufficient for this local global equivalence. So that's kind of the message of the paper. But let me proceed a little, proceed with further observations or sort of motivation for this local incentive compatibility. And you might say there are two considerations, conceptual and the other one being practical or computational. So agents may feel comfortable only while making small misreports. Perhaps there is a monitoring technology that can detect large reports or large deviations or something. Anyway, people feel comfortable making only small misreports. And there is some experimental evidence to justify this. For instance, this paper by Fischbacher and Folny-Husey, which suggests that most people do not lie optimally. That is, they do not lie in the way that best serves their purpose, but in fact, a small number do. I mean, it's like 20% or 25%, I don't remember. And this question of equivalence is useful, determines whether or not this restriction is useful for obtaining new possibilities. For instance, if equivalence didn't hold, then presumably we'd have new possibilities. We could suggest some social choice functions which are not strategy proof but satisfy some local strategy proofness, and perhaps we could recommend them to a planner. On the other hand, if equivalence holds, then perhaps the problem of characterizing strategy proofs SCFs is limited, because we can consider only the local incentive compatibility constraints, and we can formulate a relaxed problem, and which is perhaps easier to solve. So one example of that is the famous Marson paper on optimal auctions in 1981. So, the whole key to his approach is to show that some local constraints are equivalent to global ones. So we can just substitute global ones with some local ones and successfully solve the optimal auction problem. Okay. So a little bit of background. So this is the single agent case. What I'd like to suggest, and perhaps is a little confusing, that the existing literature has looked at the single agent case, because unanimity doesn't make a lot of sense in the single agent case. So, the earlier papers, although they didn't explicitly say that they were dealing with the single agent case, basically, if you don't impose any restrictions which apply to the multi-agent situation, you are in effect looking at a single agent case. So I shall just perhaps a little misleadingly just refer to all these as the single agent case. So, Carroll in a paper in 2012 and Sato, they addressed this question for the case of the equivalence of local incentive constraints and strategy-proofness. And Carroll, in fact, showed, that particular sort of salient domains, universal domain, single peak domain, single crossing domain, they all satisfy equivalence. Sato took a more general approach for models, for voting models, that is models without transfers, and provided a necessary condition and a stronger sufficient condition. We'll return to this necessary condition in a while. And we, that is me and my co-authors in this paper, in a paper which is forthcoming. So we provide a necessary and sufficient condition for equivalence, and this is called the lower contour set, no restoration property. And this is, as I said, with a completely general notion of localness. When is a type local with respect to another type? And there is some, literature on models with transfers, and I'd just like to say that these are rather different in spirit to, the models without transfers. Okay, so we consider a multi-agent model, and we assume that the social choice functions under consideration satisfy unanimity, and we show that a much weaker condition ensures local global equivalence. And sort of, pushing our approach a little further, we are also able to show the following: that this property on domains also ensures that local strategy proofness implies global group strategy proofness, and also that there is an equivalence of local strategy proofness and strategy proofness for random social choice functions. And this is actually not true for the single agent case, as I shall refer to. So again, as a remark I made earlier, so the unanimity makes, makes the local global equivalence problem trivial. I've missed out the line in the single agent case. In the single agent case, if you say that I'm always going to pick the agent's best alternative, then of course it's strategy proof, locally strategy proof, etc., etc. There's really no, there really no issues here at all. Okay, So here is the model, totally standard, at least 3 alternatives, at least 2 agents, no transfers, strip P, set of anti-symmetric orderings over A, so no ties. Ties makes life hard. So a domain is a subset D of P. And so here, unlike our previous work, we use the sort of standard notion of localness or adjacency in the literature. We don't use a general notion, but the specific sort of Kemeny notion that Pi and Pi prime are adjacent if there exists exactly one pair of alternatives that is reversed between Pi and Pi prime. You know, we use this more specific notion of localness because I think there are some issues when we look at the random thing. You know, when we prove our random result, it's not so easy if we don't have this specific notion of localness. And if Pi and Pi prime are local, then we denote it by Pi whatever squiggle Pi prime, let's say. And so in our so we are not actually using our earlier we are using a more specialized model than the one that we had earlier. And a notion that we have is an important notion is this path, which in the domain, which is a sequence of preferences where consecutive preferences are adjacent. So paths will really be very critical. Okay, hang on. Okay. So what's a social choice function? From script Dn to a random social choice function. From profiles to lotteries over the set A, script LA is a set of lotteries over A. And so our notion of local strategy proofness and strategy proofness, F is locally strategy proof at P if there exists no local deviation which will benefit agent I and strictly benefit agent I, and it's locally strategy proof if it is not locally manipulable at any P. Okay, and SCF is manipulable at P if there exists, I mean, this notion of manipulability is without reference to local types. If you can benefit by deviation, then the social choice function is manipulable, and it's strategy proof if it is not manipulable. And we can use the same definition for random social choice functions, except that, you know, we're going to compare lotteries by the, you know, by in terms of first or, you know, stochastic dominance, you know, the Gibbard Econometrica 77 paper, which I think is what most of the literature uses. Okay. And so just for completeness, the definition of unanimity, social choice function is unanimous if it picks the alternative, if there is an alternative which is ranked first by all agents, then the social choice function picks that. And in the case of random social choice function, this alternative is picked with probability 1. Okay, and so we can define our notions of equivalence. The domain script D satisfies local global equivalence for unanimous social choice functions if every unanimous and locally strategy proof social choice function is strategy proof. And an analogous definition for random social choice function, you know, local global equivalence for unanimous random social choice function occurs if every unanimous and locally strategy proof, sorry, it should be random social choice function is strategy proof. I missed the R in front of the SCF here. Okay, so the acronyms are ULGE and URLGE. Okay, so we're going to be interested in when equivalence holds. So let me give you an example to show why is it that equivalence can fail, and what's really at the heart of this issue? So you might say, well, if I can't benefit locally, then perhaps taking a bunch of local steps, I shouldn't be able to benefit globally. But that reasoning doesn't really hold, and let me give you an illustration as to why this is the case. Okay, so suppose this domain consists of exactly 5 orders, P1, P2 to P5, and they're written in the table below. There are 5 alternatives, A, B, V, X, A, B, V, W, Z. And they're written in a way that P1 and P2 are neighbors, P2 and P3 are neighbors, P3 and P4 are neighbors, and P4 and P5 are neighbors. Yeah. So for instance, between PI and P2, the only thing that's flipped is A and B. And between PI2 and PI3, W and Z, and between PI and P4, Z and B, and so on, and then A and B again for between P4 and P5. These are the only preferences in the domain. Now let's look at the social choice function, which is indicated by putting an alternative in brackets. So for PI it's A, for PI2 it's B, and then it's B for P2 to P4, and then B also for PI5. So notice that this is locally strategy proof. For instance, when I move from PI to P2, from PI1 to PI2, I had A, but then A and B switched places, and B becomes higher than A, so I pick B. So there's no way that this player can benefit by misreporting PI2 when type is PI1 and vice versa, right? You're getting your top in both cases. Similarly, all the way from PI2 to PI4. And what about from PI4 to PI5? Yes, again, it's strategy proof because the outcome doesn't change. So you can't locally manipulate from PI4 to PI5 or vice versa because the outcome is constant. And yet, when I look at PI1 and PI5, I can observe a manipulation because notice that A is better than B according to PI5. I can obtain A by reporting PI1, and well, that's a problem, right? So so here is really the source of the problem. So suppose A, F picks A at PI1. If B improves with respect to A at PI2, then local strategy proofness implies the outcome at PI2 can be B. However, if later in the sequence B declines with respect to A, there are 2 possibilities consistent with local strategy proofness. One is that the outcome switches to A. And there's actually, in this case, no contradiction to strategy proofness, but the outcome can remain B. And this results in a failure of strategy proofness, right? So the issues with equivalence arise if 2 alternatives switch rankings more than once along a path. And this is exactly what's happening here. If you look at A and B and the path from PI1 to PI5, A and B switch twice. It becomes AB to BA and then flips back to AB. And this is really the heart of the problem. And how to ensure, notice that if we had a path without this no restoration, then we might be able to we might be able to ensure local strategy proof, the equivalence of local and global strategy proofness. But the issue of entangling paths is really, the heart of this problem. So let me say a few words about paths with no restoration. A path between PI and PI prime satisfies no restoration with A and B if A and B do not switch relative rankings more than once along the path. So what does it mean? That if in the initial preference API. So suppose initially I had API B, and then if in the target preference I had API prime B, so A was better than B, at both preferences, then along the path, it must be the case that A remains B everywhere, right? If it didn't, then it would have to, rise above A, B would have to rise above A, and then sink back below A, and that would be a restoration. And on the other hand, if in the target path B is better, in the target preference, if B is better than A, then A and B must switch positions exactly once along the path. Okay, so this is a definition of a path with no restoration. Okay, now how do we put together these paths of no restoration is what we will discuss. So here is one definition, which is the lower contour set, no restoration property, or property L. So let's pick an alternative A, and let's pick a PI in the domain D. And the lower contour set of A with respect to PI are just the alternatives which are below A in PI. So this is the lower contour set of A at PI. And the domain D satisfies property L if for all PI, PI prime, and A, there exists a path from PI to PI prime that satisfies no restoration with respect to AB for all B in the lower contour set. Okay, so here is the critical thing, the emphasis on all. So if I look at PI and PI prime, and if I look at an A, then I must be able to find a path which has the property that it's a path of no restoration with respect to all alternatives that are below A and P. So this one path must satisfy the no restoration property with respect to all alternatives in the lower contour set. And so this is, if you will, the single agent case, or the case that that I was referring to, which is domain satisfies local global equivalence if and only if it satisfies property L. So it's a necessary and sufficient condition for local for locally strategy proof social choice function to be also strategy proof. Okay, another is something else that we showed in that paper, which I would like to mention for for reference, is that local global equivalence for deterministic social choice functions does not imply equivalence for random social choice functions. More specifically, I can generate a domain which I can produce a domain which satisfies property L. However, I can also show that I can also construct a random social choice function which is locally strategy proof but fails strategy proofness, of course, in terms of this stochastic dominance thing. Okay, so this existence of a path which satisfies no restoration with respect to all alternatives in the lower contour set is the key to local global equivalence. Again, let me emphasize that the social choice functions there are no restrictions on the social choice functions. In particular, in order to show that something is, in order to show a violation of equivalence, I can pick any social choice function which satisfies local strategy proofness but fails strategy proofness. Okay, there are no restrictions. Now, what we are going to do is, what if we also required the social choice functions to satisfy this additional condition of unanimity, the weak condition? And now we claim that a much weaker condition suffices. And this is the condition which is which we call property P, which is about pairwise no restoration. So we say that for all alternatives, for all preferences pi prime and alternatives a, b, there exists a path from, property P is satisfied if there exists a path from pi to pi prime that satisfies no restoration with respect to AB. So, by the way, here's a typo, weaker condition than property L, because in property L, I required the same path to satisfy no restoration with respect to all alternatives in the lower contour set of A at pi. So if I had two alternatives, X and Y, which were both in the lower contour set with respect to A at pi, then I would have had to have one path satisfying no restoration with respect to both AX and AY. And now it's okay if these paths are different in property P. There is no restriction that these paths are the same. So as you might imagine, it's easy to construct domains where property P is satisfied, but property L is violated. It's in our paper if you're interested. Let me say that, property P is not novel. It was, as far as we're concerned, it was actually proposed in the Sato paper, and he showed that it was necessary for local global equivalence without unanimity, but not sufficient. Right? It's not, well, he produced an example show that it was not sufficient. In fact, you need the stronger property L, which actually imposes some discipline on these paths of no restoration. You need the same path to work for multiple alternatives in the lower contour set. Right? So, now we can sort of reel off the results. So if I have property P, a domain satisfies ULGE if it satisfies property P. And, I really can't give you much of an intuition as to why this occurs, except that, basically, what we are doing is that you're trying to find these paths in a graph where the nodes are the preference profiles, and basically what this ULGE unanimity forces the outcome. It actually it imposes some restrictions on the outcomes that you can with which you can label nodes, the outcomes at these preference profile, and that just by itself is enough to deliver local global equivalence. Group strategy proofness, definition of group strategy proofness, there shouldn't be a coalition which can deviate such that every member of the coalition strictly improves, and group strategy proof if it is not group manipulable by any coalition at any profile. And the theorem says that if the domain D satisfies property P, then every unanimous and locally strategy proof SCF is group strategy proof. So it actually delivers more than strategy proofness. It also delivers group strategy proofness. And so note on the literature, Salvador has sort of undertaken sort of deep investigations of the connection, the examination of domains where strategy proofness is equivalent to group strategy proofness. It implies group strategy proofness. There's also the paper by Le Breton and Zaforetz. And let me just say that our results are independent. And they're sort of the sequential inclusion property, for instance, applies to domains with indifference. They don't impose unanimity, and they can also have different domains for different voters. So in this sense, their thing is more general. On the other hand, our property P applies to preferences and not profiles, and therefore arguably easier to check. And we start from local strategy proofness. And it sort of violates a richness assumption in the Le Breton-Zaforetz case. Okay. We also have equivalence for random social choice functions. If a domain satisfies property P, it satisfies URLGE. So every random locally strategy, any locally um, any locally strategy-proof random social choice function is also strategy-proof. Is also strategy-proof, right? The local global things are equivalent for random social choice function. Yeah, and so recall that the stronger property L does not satisfy equivalence for random social choice functions, and we pointed that out in our earlier paper. So okay, so a question, so there is a question regarding necessity. So is this property a necessary condition for ULGE? Sadly, no, and we are unable to show what that property is. Actually, I presume it will be. We presume it will be complicated, and however, we are able to show a weaker property, and that is that this domain, if you think of it in terms of a graph, it must be connected. So so think of the domain of preferences as a graph. It must be the case that you can find a path from any vertex to any other vertex using this local this notion of localness, which defines edges. Let me say that the connectedness is kind of a trivial property to show when you don't have unanimity, but it's actually not that trivial in the case of unanimous social choice function. It requires some work, actually. Okay. So let me add two further remarks, and then I'll conclude. So you might ask, what sort of domains satisfy property P? Okay. So I've already pointed out that domains, many of the standard domains, universal domains, single peak domains, etc., they satisfy the stronger property L. So I mean, property P comes for free. So what is it that property P satisfies? So we can get some insight, from a paper of Chatterjee et al. There's several authors, including me, so what we show is that domain satisfying property P and some richness property, and these are properties of minimal richness. Every alternative, there must be a preference where an alternative is, for every alternative, there must be a preference where this alternative is first rank. There is this notion of diversity, which is that there must be completely reversed preferences, a property I think which Arkady referred to in his talk yesterday. So if you have diversity and minimal richness, then domain satisfying property P must be very specific kinds, must be very specific subdomains of hybrid domains. And what are these hybrid domains? So there is an underlying structure on the set of alternatives, AM -1 to A1, for instance, and there exists an interval in the middle, shall we say, where preferences are unrestricted, but preferences on either side of K lower bar and K upper bar are single peaked. So basically what you do is that you look at a single peak preference, and then you kind of distort the middle. So, property P and these other richness properties give you some specific kinds of subdomains of this kind. That's kind of a, shall we say, the extra mileage that you can get from property P, some sort of perturbations of single peakedness, for instance. And our paper actually analyzes the structure of strategy proof, random social choice functions, and these things, and so on. So let me conclude with the literature, this thing. So in 2020, Hong and Kim have independently obtained a result which is similar to ours. Our first result, that property P implies ULGE. And so but they've used it in different contexts. The focus of their paper is sort of ordinal Bayesian incentive compatibility dictatorial domains, and sort of looking at other things. But I just wanted to alert you to the fact that that these things exist.
Okay.
That this other paper exists. Okay. So thank you very much. That's all I have. That's my presentation. I'd be happy to take questions.
Thank you. Thank you very much, Arunava. Let's have a round of applause before some questions. So Florian Brandel has a question. Florian, would you like to pose your question yourself?
Yeah, sure. So there is also work on dictatorship domains by yourself, among others, and I was wondering if there's any connection between dictatorship domains.
I didn't hear what you said. I missed the first part of your question.
Okay.
Who were the people you're referring to?
So you yourself have worked on dictatorship domains, so domains where every strategy-proof social choice function is dictatorial. And I was wondering if there's a connection between this work and what you're doing here.
Not immediately. I mean, let me just think about that. So I guess you could ask questions about sort of domains where local strategy proofness leads to dictatorship, right? I guess that's the question. And I mean, there's yeah. So I mean, there's our first paper really has really nothing to do with that question, because we don't impose unanimity, and all the dictatorial domain results rely on unanimity. So yeah, I think a student of mine was actually working on it. I mean, he told me a year or so ago, but I'm not sure I can. I mean, I'm not sure he's written up his results and stuff like that. So I'm afraid that's all I will commit to at the moment. So I'm not aware of any particular result about this.
So I don't recall the conditions that lead to dictatorship domains, but for example, if it were the case that those conditions are very similar to the ones that you impose for equivalence of local and global strategy proofness, then one could ask how much of your result is driven by the fact that all strategy proof social choice functions are dictatorial.
I mean, at first pass, I mean, I don't think these conditions are very similar, actually. If, for instance, in this dictatorial domains, most of the things I've worked on are things on how you rank first and second alternatives. That you look at the graph structure based on edges, based on that relation, and this is, I mean, and here our connections are somewhat different. These local switches could be way down in preferences and stuff like that. So there is no, I mean, there could well be connections. I mean,
Okay, thank you. Can I go for another question? We don't have too much time left, but let's.
Oh.
Is there another? No.
Well, it's.
Oh, Salvador, yeah, quick, relatively quick, because we are.
No, quick. Well, it's a bit speculative, but Morales states very bluntly that border is the least manipulable rule, which is a shock, right? But I think that in a way, the idea is, what is it? Why is it? Because people has to exaggerate a lot. in order to manipulate, has to really demean the person you don't want to get. So my question is, could you somehow create a model where this locality has a meaning in terms of social sanctions or some sort of punishments if you are discovered? I've been around with that idea for a long time, but I haven't been able to. So maybe you can.
No, I mean, the thing is, our earlier result is actually completely general. I mean, you can choose the notion of locality that you like. You can say that I'm uncomfortable, that it's too cognitively hard for me to figure out anything other than these changes. So our condition, we will have a condition, you know, we say, you give me your notion of locality, I will tell you whether there is equivalence.
Okay. Fair enough. Thank you.
In this
Thank
case,
you. I'll give you one, but out of the... Okay, thank you.
Okay, offline. Okay, Arunava, one very quick one. The domain of single peak preference on a tree, is this one of the domains where local implies global or not?
Okay. I have to be careful now. You mean with unanimity or without unanimity? So I think
unanimity.
That I don't think that that's the case. I'm not sure whether this locality, whether property P is satisfied. I'll have to check again. I'm sure one of my colleagues will have an immediate answer, but I'm honestly unable to recall it at the moment. That whether we have to check whether property P is satisfied. Of course, in the general case, I can always give you some notion of locality, because there it comes with the notion of locality, and I can give you some notion for which it will work. So whether it works for the tree thing, my guess is that property
Perhaps
P is quite. Yeah. So let me not commit. I will answer that question and say, and I will see answer that question and send it to you by email. I'm sorry.
Okay, so we start with offline discussions that will continue. Thank you very much, both of you. And now we will have a pause for another of our coffee breaks that unfortunately we cannot share with you guys, but in spirit we are there. Thank you. Thank you both.
Thank you.
Thank you.